Good evening, class. Welcome back to this other session where we are going to look at Group 5 derived drugs. That is qualitative analysis of pharmaceuticals containing inorganic drugs or inorganic compounds. So Group 5 derived drugs is what we are dealing with. Before we look at that, we are going to look at what is the goal for this specific session that we are having. So it takes us to the context or the content of what we have to cover. So this takes us to the list of elements as one of the content of group list of elements of group 5. List the group characteristics. What are the characteristics of those elements in the group, and then write electronic configuration of individual elements of that specific group. So we keep on and continue with the introduction, where we see that group 5A elements including nitrogen, phosphorus, arsenic, antimony, and bismuth are of interest in medicine. The outer layer of their atoms have 5 electrons. That qualifies them to be in group 5 of the periodic table because they have 5 electrons in their outermost shell. Or another word for this outermost shell, we also call it the valency energy level or the valence shell, whereby we find that all elements we can derive their valencies from by looking at how many electrons are in their outermost shell. For example, in group 7 that we already looked at, we saw that it has 7 electrons. However, for group 7 we got 8 minus 7 because we know the maximum should take 8, so it took the valency of 1. For group 6 as well, we see that we subtracted 8 from 6 and we got a valency of 2. However, for group 5, it has 2 valencies. One, when we take that in the outermost shell, how many electrons are contained in the outermost shell, and when we get the maximum electrons that a valence shell should cover to contain or to obtain the noble gas structure. So you find that 5 plus 5 is for this 5 electrons that we have in the outermost shell, and then we have 3 because when we subtract 8 from 8 minus 5 we get 3. So they exhibit both positive and negative oxidation states. So this is plus and then this 3 is minus 3. Give it a correction. So we have here minus 3. So we see that it has 2 oxidation states, plus 5 and minus 3 as their oxidation state. They generally have a lower electronegativity and their hydrogen compounds are less polar. So electronegativity, we know that is ability of an element to attract electrons that it is sharing in a covalent bond, or that it has used in participation of a bonding or in the process of bonding, because all elements of periodic table participate in chemical bonding in order for them to become stable. So when they participate, there will be need, or there will be situation where they will need to bond with others or even remain the way they were. So you'll find that there will be need for them to pull out electrons from those specific bonds that they have already shared. They can either share, they can either gain electrons from another element of the periodic table, and all that takes us back to bonding. So we see that these group 5 elements of the periodic table have a lower electronegativity and their hydrogen compounds are less polar. Therefore, they do not detach hydrogen ions in aqueous solutions, and consequently they are not acidic. So these elements, we know that an acid is a proton donor, so we expect an acid to release or to give us out a hydrogen ion. So with the group 5 elements of the periodic table, they are not in position to detach, they are not in position to release, let me call it release, the hydrogen ions that they have in their aqueous solution. So since they do not donate a proton, they are not able to release a proton, you find that we cannot call them acids because an acid is a proton donor. It has ability to release or detach hydrogen ions. So here we have a compound, a structural compound. I think most of us have seen these cylinders either somewhere or at least in the hospital setting. We have seen these cylinders somewhere. So these cylinders, we can have some of them containing oxygen, but this specific one has nitrous oxide. So nitrous oxide is one of the compounds of group. Leave alone the elements. We already looked at elements as nitrogen. We also saw phosphorus, but now we are looking at the compounds of group 5 elements of the periodic table. Nitrous oxide is one of the compound, and we can pack nitrous oxide in containers that look like this. However, let us look at how we can prepare our nitrous oxide. So method of preparation, we have roughly two methods of preparation. One is when we prepare preparation by heating ammonium nitrate at about 200 degrees centigrade. So we heat ammonium nitrate, this is ammonia and then this is a nitrate. So when we have these two compounds combined, we see this is ammonium nitrate. Let me try to zoom this so that we can see the equation of reaction very well. So this is how it is. This is ammonia, and then this is our heat, or the degree at which we can heat ammonia to give us nitrous oxide. So it gives us both nitrous oxide and water. This is the equation of reaction that you need to know, and it is a well-balanced equation of reaction. The second method we have to look at, or we have to know, is preparation of pure nitrous oxide. It's prepared by heating sulfamic acid with 73% solution of nitric acid. So here we are heating the two acids, and the equation of reaction is not clearly given because there is a vigorous reaction taking place, and as well we see that we may have a number of impurities, but 73% concentration of nitric acid, of nitrous oxide, can be prepared in this different way. So when you are asked to outline method of preparation of nitrous oxide, you can give either of the two methods. If you are asked to prepare nitrous oxide from ammonium nitrate, you give this preparation and then you write for us equation, or you outline equation of reaction so that you are in position to get all your marks. So after we have known how we can prepare nitrous oxide, there is need for us to know the different properties of nitrous oxide. So the next slide takes us to properties of our nitrous oxide. Nitrous oxide, it is a colorless gas with faintly sweetish taste. So here we see that it has a sweetish taste or sweet taste. It is heavier than air and supports combustion. So you find that nitrous oxide is heavier than air and it can support combustion. Supporting combustion is like aids burning, like how we looked at oxygen in group 6 elements of the periodic table. It also has this property of supporting combustion. So one of the things where we see this supporting of combustion happening is when a glowing splint is placed in a blast into flame. So we see that it ignites a glowing splint or relights a glowing splint. When mixed with nitric oxide, no red fumes are produced. So that makes it different from oxygen. So we know that oxygen also relights a glowing splint. and then nitrous oxide as well. Here they are telling us, or we have to know that it also really lights a glowing splint, but we need to know the difference. The difference is, if all of them relight a glowing splint, how do we separate one from the other? How we can separate one from another is when we mix it with nitric oxide. We see that no red fumes are produced. This should be nitrous oxide, not nitric oxide. Nitrous oxide. When mixed with nitrous oxide, no red fumes are produced. So when we have a glowing splint and then we expose this glowing splint to nitrous oxide, we do not expect to see red fumes or flames. Let's call them flames. We don't expect them to be seen. We know we have two types of flames. We have the sooty flame, and then we have the blue flame. Okay, so with oxygen we expect that sooty flame and can be red in color, but now with nitrous oxide we do not see something like that. Another property we have is it dissolves well in water and has a characteristic odor. We talked about the sweetish taste. So we also expect it to have a specific smell. We expect it to have that specific smell. So after we have known its properties, there is need for us to know how we can identify the presence of nitrous oxide. So still here we see that a glowing splint bursts into flame on being plugged into the gas. So like those cylinders we saw up, when we expose a glowing splint to, or when we open up the gas from those cylinders that we saw in the previous slides, so and then we have our glowing splint, we expect it to blast into flame or burn much, too much. So when mixed with an equal volume of nitrous oxide, no fumes are produced. This takes us back the other side, so for us to be in position to distinguish between nitrous oxide and then oxygen gas, since all of them relight a glowing splint. So let's see how we use and store nitrous oxide. Sorry about that. How we can use it is used as a general anesthetic and then analgesic. Anesthetic is when we administer a medicine to patients who are going to be operated. I don't want to call it half dead because I'm trying to get another word for anesthetic. So majorly we use it for general anesthesia, and then it is analgesic property. Analgesic is another word I can use for it, is painkiller. So we can use it as a painkiller, but don't go and get for your patients this. You find it is compounded with something else, or it is added in something else, not necessarily how it is as a gas. So that you need to put in mind. It is stored, this is now the storage, it is stored in a metal cylinders in special cool room free from materials of inflammable nature. The whole cylinder should be painted blue. Those colors we saw, we can call it navy blue, or someone can call it black. The name of the glass labeled on let me see this, on the shoulder of the bottle. So let us go back to the slide that gave us, sorry about this. Let's go back to the slide that gave us this. So when we zoom this, let me try to zoom it and we see the color that it is. Can we see blue? Can we see black? Can we see navy blue? The answer, you know it, depending on how your sight is good. As for me, I am seeing this is navy blue. That's what I see. Others may see black, but I see navy blue. Never mind. but you need to store it in a blue cylinder, just like what we see there. It is necessary for us to pack it in such a cylinder. Okay, and then we have to look at what in case of poisoning, in case a patient, we have overdosed the patient with nitrous oxide, how do we manage it? So we call such a case poisoning, or in case not really overdosing, but in case we see that maybe some patients got exposed to nitrous oxide and they have inhaled much of it, or they have in whatever way they have tried to use it, it has been administered much. So in case of nitrous oxide poisoning, we need to manage the patients. In poisoning, the patient should be kept warm and artificial respiration applied. So artificial respiration is when we use our oxygen gas to respirate a patient. Where poisoning occurs from swallowing, this is some of the few ways how this poisoning can take place. This is by swallowing. A patient can swallow. Like we said, it can be used as an analgesic or a painkiller. So a patient can swallow it, like swallowing, and then it can be through gastric lavage. Where poisoning occurs from swallowing, sorry about that. Let me repeat myself. Management of nitrous oxide poisoning. In poisoning, the patient should be kept warm and artificially respiration applied. Where poisoning occurs from swallowing, gastric lavage should be used. So if it is not as a result of swallowing, if a patient did not swallow it, then there is need to keep the patient warm and artificially respirated. But if it is as a result of swallowing, like a patient swallowed it, the patient ate it, let's call it eating. So if a patient ate it, there will be need for us to have this gastric lavage to be given to the patient. Alright, so after we have known the use, we need to know the different quality control. Quality control, like the other time I was saying, it can be like if after we have prepared from those different methods of preparation, after we have prepared it, how can we know it is pure, it is of quality? And how can we recognize it is of quality? How we can know is when we carry out tests, when we sample out whatever we have manufactured and we carry out tests on it. And when we are testing, we have things that we need to check. So those things that we need to check are what we call parameters. For example, if you are making juice, let me use juice. If you're making juice, after you have made juice, you're going to test, so that becomes a parameter to check whether the sugar is enough, or you're going to see the thickness, you can be seeing it, and then the color of the juice, you are also seeing it, how uniform you have mixed the sugar, in case you didn't blend the sugar together with with your fruits, you find that it is the same stuff. Like it becomes a parameter what you're checking out to identify the quality of a compound. So this quality control we are carrying on our nitrous oxide, because we want to see from the different methods we use for preparing, is it of quality? And if it is of quality, does it have any impurities? Okay, so these are some of the things we are going to look out for, or these are some of the impurities that we expect to be together with our nitrous oxide. So we have parameters as tested by the BP. This is the British Pharmacopoeia procedures. A British Pharmacopoeia is a documented reference book that we always use for manufacture of products. It can be medicine, it can be raw materials, because you can even manufacture raw material that can be used for manufacturing of medicine. So here we see that acidity, we look out for acidity or alkalinity of our nitrous oxide gas. And then we have halides and then hydrogen sulfides. We also look out for them. We have arsenine and phosphonin. We see that arsenine and phosphonin, these are derived from those other elements that we have in the periodic table of group 5, because one of them was arsenic and then phosphorus. So this is derived from arsenic and then phosphorus. Another thing we have to look out for the presence of carbon monoxide in our preparation, and then a nitric oxide, and then our nitrogen dioxide. Then we have water and carbon dioxide. So we have gone to, that marks the end of one compound of nitrogen, that was nitrous oxide. So here we are going to look at another compound of nitrogen of group 5 of the periodic table, which is sodium nitrate. So this is sodium nitrate. Sodium nitrate has a chemical symbol of capital N smaller a, capital N, capital O, and then we have a 3 down. This is sodium nitrate. So here is a diagram showing how sodium nitrate can look like. So this is our sodium nitrate. Okay, I don't know whether this is visible. Sorry about that. Let me see. Okay, let's just picture this. So what I see, I can derive properties from what I'm seeing. I can see white crystalline solid, so that can be my one property. And then of this, I can say a white solid, actually crystalline, because I can see things like crystals, so I can derive it that way, white crystalline. And then those other properties come if I am able to test. Of course, we may not risk to test sodium nitrate, but if we are in position to test, we can say maybe it is tasteless. I'm just giving an example. Can be tasteless. Sometimes we may find it has no odor, but we are going to look at those properties as we move down the presentation. However, this is how sodium nitrate can look like. All right, after we have seen how it looks like, let us come and look at how can we prepare sodium nitrate. We have preparation of sodium nitrate. We have a number of ways we can prepare all these compounds that we look at in all the different groups of the periodic table. So this can be prepared from nitric acid. How? We need to have a carbonate reacting with nitric acid, because we know a carbonate, we see that sodium nitrate is prepared by neutralizing nitric acid with sodium carbonate or sodium bicarbonate. So this is a structure of sodium carbonate, a chemical symbol of sodium carbonate, capital N, small a, capital C, capital O, and 3. So you see that this carbonate has a valency of 2, and then sodium has a valency of 1. So we expect to have a 2 down there. Sorry about that, but that 2 should be in small, should be a small 2. So take that as sodium carbonate reacting with nitric acid to give us sodium nitrate. Of course, we had, let me return this, but when you write down in your notes, make sure you put the 2 in the middle of sodium and carbonate to give you sodium nitrate. Sodium nitrate, nitrate has a valence of 1, and then sodium has a valence of 1. So we expect to see something like this. And then water and carbon dioxide gas. So you can as well be asked to identify the gas evolved. So the gas evolved, we all know that we need lime water. So another word for lime water, or a chemical name for lime water, is what we call calcium hydroxide. So we expect when we pass carbon dioxide gas through lime water, we expect to see a turbid solution, or we all expect to see what we call a milky, some people call it cloudy, or some books call it cloudy. So you can be asked to prepare sodium nitrate, as well as identifying the gas evolved. So you need to know which reagent to use when you're identifying the gas evolved. So this is our equation of reaction. Let me try to zoom it. This is our equation of reaction. Our equation of reaction, we have sodium carbonate reacting with the nitric acid to give us sodium nitrate, water, and carbon dioxide gas. So that is one method of preparing. As simple as that. Don't complicate life. Just find something that works for you better. Okay. The second method of preparing our sodium nitrate, sorry about that, sodium nitrate, we prepare it from ammonium nitrate. So sodium nitrate can be prepared by mixing stoichiometric amounts. Stoichiometric amounts may confuse people. We are going to look at it more. We are going to have another presentation on different methods of assay and what they mean. So stoichiometric, we can have an I here instead, not behind, to make the correct stoichiometric amounts of ammonium nitrate and sodium hydroxide. So sodium carbonate or sodium bicarbonate. So here still we have two things. We see that we use ammonium nitrate in the presence of sodium hydroxide to give sodium nitrate, and then ammonium hydroxide as one of the ways we can prepare it. And then we can also have we can either use sodium carbonate or sodium bicarbonate. I forgot to tell you how a bicarbonate looks like. So this will be a carbonate if it had a 2 here. And then if it is a bicarbonate, we shall have H, should be up top H, should have a H in the middle instead of the 2. This is a bicarbonate. This is sodium bicarbonate. Without it, it is sodium carbonate with a 2 there. Okay, so make sure you note that. So equation of reaction, let me try to zoom it so that we can see it. Sorry, this much. This is so small. Alright, I don't know whether this is clear. Hope we can all see this. Sorry. Let's look at this. I want to see the equation of reaction. This is very vital and necessary for us to see it well, because we shall be asked to write it, and you need to write a well-balanced equation of reaction. Alright, so this is it. We have something like this. Oops, sorry. Bad news. Sorry about that. So we have this. I think this can be seen because I'm trying to zoom it and it's instead going to another slide. So this is the equation of reaction, well-balanced equation of reaction. Always make sure that you have balanced your equation. Whatever you write, make sure it is well-balanced. Okay. All right. Properties of our sodium nitrate. It is a white crystal. We were talking about it, like we were seeing it up there, and then we were briefly trying to give it its properties. Now the real properties are here. So we see that it is a white crystalline substance with a pale yellow tint. We saw how the tint was. Let me go back. All right. So we see that we would see a yellowish thing, and what this is what they are calling a tint, or what we call tint. This is much better. So we see this as a white crystalline solid with a yellowish something in it, like it has that yellowish bit. So this is what this is what we are getting its property, our sodium nitrate. Okay, at least don't forget this, because it is clearly seen here. Don't forget about it. All right. So we come back to properties. This is really too zoomed. Readily dissolves in water, because the other property we have already looked at it, where we said a white crystalline substance with a yellow tint, and then we have readily dissolves in water, and then we see that it is hygroscopic, meaning it absorbs water from the surrounding, from the surface. So when we leave it open, that's why we say that the cover is black, so that it does not allow any light or any in water something. That is why we see that it had a black lid, a cover. So it is, since it is hygroscopic, and then it exhibits both oxidizing and reducing properties. Do we remember where we saw something or a compound that exhibited both oxidizing and reducing property? We saw it in group 6 elements of the periodic table. Their compounds. That was to be more specific, that was hydrogen peroxide. It had both oxidizing and reducing properties. Okay. All right. So that's all about properties. Let us look at identification tests or qualitative analysis of this is quantitative analysis of our sodium nitrate. Sodium nitrate is identified by detecting sodium ions as well as nitrite ions separate. So for nitrite ions is detected by reaction with diphenylamine in an acidic medium to form an organic bright blue dye. So this is observation. So the reagent is a diphenylamine in acidic medium. And then observation is a bright blue dye is formed, organic bright blue dye is formed. And then we can say or confirm a presence of nitrate ions. This should be a A. These are two different things. We have nitrate and nitrite. And nitrite. So we confirm presence of nitrite ions. And then we have colorless crystals or mass of yellowish rods. That is hygroscopic. Sodium ions, we talked about them when we're looking at group 7 elements of the periodic table. We identified, we used a specific reagent for sodium ions. If you don't remember it, what we used was, we used zinc uranyl acetate in the presence of acetic acid. So when we use that to identify the sodium ions, we mix it in solution. So after we have mixed it in a solution, if sodium ions are present, we expect to see a yellowish or a yellow precipitate. If they are absent, we have no observable change. That is for sodium ions. So you can be asked, why have I have not repeated it here? Because we already did for sodium ions. So we are just looking at the nitrate ions separate. That is why we are focusing on that. But when you are asked to carry out identification test for sodium nitrate, make sure you identify the nitrate ions and then the nitrite ions separate. Identify the nitrate ions and the nitrite ions separate. Okay, where sodium is the same, zinc uranyl acetate in acetic acid. Observation, yellow precipitate, and then conclusion will be sodium ions present. If there is no observable change, you will say sodium ions absent. When you're always giving this, give in a two-way form, when it is present and when it is absent in solution. Okay? All right, let's look at assay, pharmaceutical assay. Pharmaceutical assay, we said another word for it is qualitative analysis, and another word for qualitative analysis is titration. Okay, so here they are giving us what do we need to add, what do we need to have when we are carrying out this specific titration. Okay, there is need for us to know what we are adding, what we need. So here the first thing is we have to dissolve 0.4 grams in 100 ml of water, or you can say dissolve sodium nitrate, because we saw the sodium nitrate in crystal form, and titration cannot be carried out when it is in crystal form. So we first dissolve it to form a solution, and then we shall pick 20 ml of that solution while stirring continuously and keep the tip on the pipette below the surface of the liquid into a conical flask. So you pipette out 20 ml of whatever you have mixed into a conical flask. After, you need to have a burette, and what you're putting in a burette is what we call ceramic sulfate. And how many mils? You are picking 30 mils, or you are putting 30 mils. So this is what happens: ceramic sulfate, and then you have your you have your sodium nitrate. So this, after you titrate, of course this 0.1 molar, always the main aim of titration is to move from the known volume to the unknown. The known here is 0.1 molar. Like for it has its molarity, and we shall be looking out to know the molarity of also sodium nitrate. So we move from the known to unknown. Since we know this, we need to now find out the unknown, which will be sodium nitrate. However, I'll organize a class for this specifically so that we understand it in depth. Uses and storage of sodium nitrate. Used in treatment of cyanic poisoning, and then stored in airtight containers. That's how we can store it. Next is what we call arsenic poisoning. Arsenic was one of the elements of this group of the periodic table. So you should know how to write its chemical symbol. You should also know, apart from writing its chemical symbol, you should also know how to write its electronic configuration, know what atomic number it is. Arsenic enters the body as inorganic arsenic salts. Major routes of absorption include the gastrointestinal, respiratory, that's the GIT, and then respiratory, that is all mucosal surfaces. You know that respiratory has the mucous membrane, the gastro has that mucous membrane. This takes you back to anatomy. It distributes predominantly in soft tissues, that is highest in liver and then kidney. This is how it gets distributed, and this semester we are doing pharmacology, and in that pharmacology you have to understand how medicine gets absorbed, how it is metabolized, how it gets distributed, and how it gets eliminated. So this is showing us for this specific arsenic compound, it gets absorbed in the GIT and respiratory and other mucous surfaces, and then they have not given us much about how it gets metabolized. However, it is distributed predominantly in soft tissues, for example, the liver or the kidney, and then avidly bound in the skin, hair, and in nails. So major clinical manifestations include cardiovascular, When a person experiences this type of poisoning, we have how it affects, and we have said in the cardiovascular system, in case it affects the cardiovascular, it brings about shock, and then we have arrhythmias when the rhythm of the heart changes. That is a condition called cardiac arrhythmia. However, in the CNS, that is the central nervous system, we expect an encapsulopathy, and then peripheral neuropathy. And then for the GIT, we expect what we call gastroenteritis. Sorry, we have already gone. We are going to look at those. We see we have gastroenteritis, and then we have, sorry about that. Stay hold. Oops. I think when I try to reduce that, and then we see what we can do. We have pancytopenia and then cancer. This you need to know about them. When you enter deep into pharmacology and therapeutics, you'll be in position to understand all this. So we have said we have here dermatologic lesions associated with chronic ingestion of arsenic in drinking water. In case arsenic is much in drinking water, we expect a patient to have these lesions on the skin. This is how they look like. These are the lesions. Some people can call this rash. So it portrays that there was poisoning. There was much of arsenic in the water that people took, and it brings about this reaction. Someone will come and tell you, I just took water and this started coming on my skin. Not every rash or lesion we see on the skin is as a result of arsenic poisoning. So don't go out there and manage every sign that you see as this as arsenic poisoning. Okay, make sure you examine the patient well, and make sure that you carry out specific tests to find out what is the cause. Okay. However, this is how arsenic poisoning would affect the skin. So we have mechanism of toxicity and management. It inhibits enzymes or interferes with oxidative phosphorylation, and then where it alters the cell signaling, and then also it also alters the gene expression. So we find that this arsenic poisoning is a big deal, and it needs proper management and quick management. Okay, like you have to handle your patient as soon as they present with these conditions. So for acute poisoning, treatment is based on appropriate gut decontamination. Like make sure that if it is they swallowed it, make sure you decontaminate the gut. The gut is the stomach, or the GIT. Intensive supportive care is needed, and then prompt escalation with the Onithiol 3 to 5 milligrams per kg intravenously every 4 to 6 hours, or you can use dimethyl 3 to 5 milligrams per kg depending on what weight your patient is. This is the management. Intramuscular every 4 to 8 hours. So this we see that we use the IM route, intramuscular. Here we are using IV, intravenous. These are routes of administration. We have oral route, let me not go back to pharmacology or deep in pharmacology, but briefly you need to appreciate that we have different routes of administration. We have the oral route, and then we have the topical route. We have the parenteral route, where parenteral is divided into intravenous and intramuscular routes of administration, and then those other routes of administration that you may explore more in pharmacology. So this is a continuation, and it brings us to the end of group 5 of the periodic table. So here we see that management of chronic arsenic poisoning consists primarily of termination of exposure and non-specific supportive care. Make sure that if it is brought as taking a lot of water, make sure that, taking water with a lot of arsenic in it, make sure you discontinue or stop a patient from taking that water. Like, look at what the cause was, how did the patient get exposed to that, and make sure that it is discontinued. Like, stop the patient from doing whatever made them have that, that they have presented to you. That is why we are saying primarily termination of exposure. Exposure becomes, is it from drinking water? Where did they get it from? Stop it. Tell them to stop whatever they use. And non-specific supportive care. Like, you don't have to be specific on which care to give. Do the management bit of care and then advise your patient accordingly. So I want to thank you so much for listening to me. This marks or brings us to the end of group 5 elements of the periodic table, as well as group 5 compounds. So briefly, to go through them, we looked at elements of group 5, and in elements of group 5 we looked at we have covered majorly 2, that is nitrogen and arsenic. So with the nitrogen, we see that we looked at the compounds of nitrogen where we have nitrous oxide, and then we saw nitrogen oxide, and also we looked at how we can prepare nitrous oxide as well as how we can prepare nitrate oxide, sodium nitrate. Make sure you do not forget that. We can also have sodium nitrite with I, leave alone the A. So we can have sodium nitrite or sodium nitrate. Make sure you have it at the back of your mind, and you can briefly summarize it, and any question that comes up or that you will interact with in group 5 elements and these different preparation, I hope this video can enable you answer it. I want to say thank you so much. Please subscribe to this channel for more videos like this. Thank you. Asante.